In this video, we want to address the question that's of pretty utmost importance here to quantum mechanics, and we want to ask, where is the electron? Now, of course, we know that we can't ask that question because of the Heisenberg uncertainty principle. If we know the energy of the electron, which we do, we can't know where it is, but we can know where it's likely to be. And so there are a lot of different ways to go about this, and this problem isn't as intuitive as maybe some of the other problems, like trying to figure out the equilibrium bond length or anything like that. So first, if the first way to approach this problem is the way that we approached many similar problems in the past. And if we wanted to find the probability of finding the particle within a certain region of the box, we would just square the wave function, take the complex conjugate, multiply it by itself, and that would give us our probability density. We integrate that over our region of interest, and that would give us what we want. So we can certainly do that here for the hydrogen atom as well. So we can take the complex conjugate of our wave function, multiply it by our wave function again, and what that gets us is 1 over pi a naught cubed. We're going to do this with a 1s orbital, and then e to the minus 2r over a naught. So we get this function. And what we can do with this function, we can do two things. We can, like we've done before, we can take or integrate this with respect to r over whatever window and find the probability of finding our electron within that certain region. But we can also just plot this function and get an idea of where the electron is more likely to be. So that's the approach we're going to take here. I'm going to sketch this out. If we plot the probability here, this is our function squared. As a function of time, what we end up getting is something that looks like this. And this is a little bit strange to how we think of the electron. So from Gen Chem on, we've been told that the electron exists in this diffuse cloud outside of the nucleus. But here, what this is showing us is that we have the highest chance to find our electron at r equals 0, which would be in the center of the nucleus. So that's a little bit strange. And that's because this isn't exactly the best way to go about this problem. So by doing it, by going through this problem in this way, we have ignored the angular component. And what we're really asking is, what's the most likely radius to find the electron? So if we can find the electron to one angle and we say where you're going to be, it's more likely to be in the center. But the electron is, of course, not confined to one angle. It's free. It can go all the way around our nucleus. And this matters because if we imagine, so we can think about the s orbital like we have here, but this is true for all of the orbitals because they're spherically symmetric, is as r gets bigger, as the radius gets longer, that sphere also gets bigger. So we can think of that, we can think of the surface area of the sphere, and that is equal to 4 pi r squared. So we need to modify this r function by a parabola to kind of figure out where this is likely to be. So even if the most likely point is in the center of the nucleus, that's just one point. And then if we say take a step that's maybe one Bohr radius a naught away from the nucleus, now we have a whole lot more points that are on that sphere, and so on. As we get bigger and bigger spheres, we get further and further away, we have more spots. So there's more potential spots that have that radius. So there's actually a maximum value that's not at the nucleus. And how do we find that? Well, to find that, we take this probability distribution function. And so what that is it's going to be, we're going to integrate over all of our area, all of our angles. So we have the integral from 0 to pi, 2 pi, and then I have the integral from 0 to pi. And then we have, again, our psi star psi. But what we have is the bounds of integration. So what are the bounds of integration for spherical coordinates? They're not dr d theta d phi, rather they're r squared sine theta dr d theta d phi. And this is the problem that we had to solve. So this is going to account for our spherical nature of the 1s orbital, and it will account for the variety of other shapes of orbitals we get as well. So lo and behold, when we do this integration, when we integrate sine theta d theta d phi from theta from 0 to pi and phi from 0 to 2 pi, we end up with simply 4 pi. So we have 4 pi r squared times the square of the magnitude of our wave function, which is simply multiplying our function from earlier by the surface area of the sphere. And so this will give us 4 over a naught cubed r squared e to the minus 2r over a naught. So this is now a function that we can plot. And what this looks like, I'll draw it down here. So if we're plotting this as a function of r, here what we're plotting is a little r squared times our big R squared as a function of r. And this function has the following shape. It goes up sharply and then kind of comes down less sharp. And we can see now that this is a function that's much more like what we would expect. So we have a radius for the most expected position that is not in the nucleus. We have some maximum r value that's not 0. And we have also a spread, like is consistent with this idea of not exactly knowing where the electron is. So from here, there are 2 questions we can ask that are similar, but they're slightly different. And the first one is going to be, what's the most probable value to find the electron at? And we can tell from the graph that that's simply going to be this maximum here. And how do we find the maximum? Well, we take the derivative of our function and then find whether that equals 0. And that's going to be our maximum or minimum. So we can do that. So we need to take the derivative with respect to r of our function up here. So that's going to be, so that's the derivative of 4 over a naught cubed times r squared e to the minus 2r over a naught. So that's simply going to be 4 over a naught cubed, and then we do the product rule. So we have r squared times the derivative here, which is minus 2 over a naught e to the minus 2r over a naught. And then plus e to the minus 2r over a naught times 2r. So here we're going to be able to factor out e to this whole term here. So we can factor out 2r e to the minus 2r over a naught. We can do that. So we'll factor that out. So I'll get an 8. So I have 8r over a naught cubed e to the minus 2r over a naught. And what's left inside is going to be minus r over a naught plus 1. So here, this function will equal 0 when r is equal to a naught. And so that means this value of a naught is our most likely position to find the electron at. And this is corresponding to the Bohr radius, a naught. The other question we can ask is, where is the electron on average? And that's a slightly different question. So where the electron is on average is the expectation value, which is essentially when does the area under this curve here end up equaling a 50%. So what's that midpoint, which is not the most probable value. And we calculate that in the same way we always calculate expectation values. So the expectation value is going to be equal to the integral from 0 to infinity of our wave function, times our wave function that's been operated on by our operator of interest. Here, our radius operator is just r. Now, I'm writing this out here as a single integral because I have already done the double integral up here. If you hadn't already done the double integral, you would need to do a triple integral over all 3 of our variables. So this then is simply 4 over a naught cubed times integral of 0 to infinity of r cubed e to the minus 2r over a naught. And this is an integral that you can solve by parts if you're feeling like punishing yourself, or you can go look up in an integral table what the solution to this is. And the solution is going to be 4 over a naught cubed, our constants. And then we multiply that by the power of our r factorial, so 3 factorial, and then over what we're raising, so over 2 over a naught, we're raising e2 raised to our 3 plus 1. So 2 over a naught to the 4th. And you go through and solve this again. We can simplify this. We get 4 over a naught cubed times 6 a naught to the 4th over 16. And with a little bit of condensing here, we can realize that this is 3/2 A naught. So on average, we would expect to find our particle, our electron, at 1.5 A naught, even though the most probable value is A naught. So these are 3 different ways to, again, to talk about where the electron is. The first one is typically not super useful because it ignores the angular components. The other 2 are equally useful. It includes the angular components, and it can ask, where is the most probable value, which is at the peak there, and then the more likely value is a little bit further away because this is not an even curve, so that it's a little bit right shifted, has that shoulder there. And with this, we're able to figure out these problems, and we could apply this to any orbital we wanted to figure out where the electron is in any given orbital.